putting together a wonderful program and for the invitation to come and give this talk. At the offset, I like to apologize that I got the date wrong, but hopefully this will be hopefully this is the last of the errors in the slides. So I'm going to be reporting a new class of topological phenomena. I call it that way for a particular reason, protected by a certain class of textures which we name diabolical textures. So let me just give an overall summary of what this talk is going to be about. So this will be a talk about a new class of gap states of free and interacting systems, and a necessary component of these states are that it needs to have broken translation symmetry. So it needs to have, it's in the presence of a special class of textures which I'll be describing, and these textures embed charge pumps in the generalization in various dimensions. And I'll argue that these textures protect a new class of states, and eliminating these textures produce a new class of critical phenomena. I'll demonstrate everything using a free fermion example in 1+1D because it's just so easy to state. But then I'll also generalize to arbitrary dimensions, symmetry classes, interactions, and the rest of it. So this is work completed with Sayantan Mandal and Nilima, who were both visiting students at HRI, and the results are present in this preprint that was put out a month or so ago. So if anybody is interested, I welcome you to read it. Okay, so let me begin a couple of statements about relevant ancient history. So in condensed matter physics, we are interested in understanding various kinds of many body phenomena, but there's a particular limit where this becomes very easy to track, which is when we can describe these phenomena using free fermions, non-interacting fermions. So in this case, there are a collection of single particle energies which one can understand relatively easily, and these single particle energies organize themselves into different bands. So depending on whether the many body state is constructed by occupying a complete or partial set of bands, we get insulators or metals. So this is what we learn in condensed matter physics 1. But the interesting thing about the last couple of decades is that we understand that even when you have a single filled band, the filled band could have various distinct topological characteristics which result in distinct phases of matter, most famous one being topological insulators. And the different ways in which topology can be imprinted on the band, if you want to change it, then it has to necessarily undergo a bulk gap closure, in other words, a phase transition. So a monumental achievement of this program is that one can actually classify the different ways in which we can have topological characteristics for a band, and this table encompasses this information about, in a certain dimension for a given symmetry class, how many distinct ways can we have topological character for a band. Let me just make a mention that typically when we study band theory using Bloch's theorem and the rest of it, we usually consider systems that are homogeneous. There's discrete translation invariance of some sort. But this is actually not necessary to achieve this classification. There are more powerful tools like symmetric spaces and so-called K theory that gives you the answer even without requiring a system to be homogeneous. But this homogeneity gives an enormous simplification. So in the presence of translation invariance, we can invoke Bloch's theorem, where we can organize a single particle energy, single particle states using the quantum number of a Brillouin zone, the crystal momentum, which takes continuous values on a 2 torus or 3 torus or 1 torus. So one can introduce invariants that we can assign to the bands, the way in which your Bloch states twist and turn as it moves around the Brillouin zone. One famous example is the so-called Chern number. But even outside the Chern number and the entries of this table, in the presence of translation invariance, you actually get more. You get new classes of states that go by the name of fragile topological states and weak topological states. Right? So this talk in some sense is going to be the complement to that. So this will be a class of states that are present only in the absence of translation invariance, where you cannot use Bloch's theorem. So I said I'll demonstrate everything using a particular one-dimensional example, and then move on to the generalization to different dimensions. So the example that I'm going to be using is the so-called Rice-Millet model. So it's a model of 1+1 dimensional hopping fermions where there is a dimerization to the hopping amplitudes. So on even and odd bonds, the fermions hop with different amplitudes. And then there's also the presence of a staggered chemical potential that favors or disfavors the fermions from being on one of the sublattices. So this Hamiltonian has a rather trivial phase diagram. So the phase diagram is schematically represented here. So if you tune the hopping amplitude and the staggered chemical potential, there's exactly one phase of matter which is smoothly connected to each other. But there's one interesting feature which is at the very origin, when you tune both of these parameters to 0, we have a one-dimensional metal, so it's a gapless state. So apart from this one gapless state at this one particular point, at least at half filling, which I'll focus on for most of this talk, the entire phase diagram consists of a single very trivial atomic insulator. So the symmetry of this model that I'm going to be focusing on is charge conservation. Everything else is dispensable. The important thing about the Rice-Milling model is that it gives you a Hamiltonian from which you can extract what is known as a Thouless charge pump. So if we slowly tune the parameters such that the dimerization and the staggered chemical potential sweep a circle that encircles this diabolical point, this gapless point, which I'm going to be referring to as the diabolical point, what you obtain is a Thouless charge pump, and we can understand this by going to extreme limits. So let's just track this particular fermion over here, which at large staggered chemical potential begins in site number 1. As you go here, it gets delocalized in the bond between sites number 1 and 2. You come here, it went to site number 2. Then it gets delocalized between sites 2 and 3. And then you come all the way around, it's gone from site number 1 to site number 3. In other words, it's shifted by one unit cell, and this is precisely what a charge pump does. The question I'm going to be asking is, so the way one does this is we tune the parameters very, very slowly in time so that we can invoke the adiabatic theorem. So the state, if it begins with the ground state, continues to remain in the ground state because at no point does the spectral gap close. So we can always have a rate at which we can tune the parameters slowly enough so that we always remain at the ground state. What I'm going to be doing is basically asking, instead of making this variation in time, what will happen if I make the variation in space? So I literally copy the same model as I had before, but now the parameters, the bond dimerization and the staggered chemical potential, this slowly varies in space. I do the exact same thing. I take all of these states corresponding to the circle that encircles the gapless point and slowly vary it such that at any point the variation is 1 over L, as you see over here. So in the thermodynamic limit, an ant that is sitting at one point of the chain basically sees a homogeneous system with fixed parameters. On the other hand, the gap does not close, so everything can be slowly adiabatically connected to each other, so the entire thing is one well-defined gapped state. Caricature-wise, on one end, the fermion system looks like the fermions are living on every other site. Then slowly the fermions go delocalize between the dimers, shift sublattice, and then come back all the way as you go from one end of the chain to the other. So this is the system that I'm going to be looking at. It's a spatial version of the Thouless charge pump. There's a very illuminating way to see the same thing, and this is results from another paper that I've written with Sashank Singham Reddy and Nick Jones. You can actually take this phase diagram of the Rice-Milling model and do something that's very commonly done nowadays, which is take the band structure at each parametric point and compute the Berry phase. Now the Berry phase is some angle valued thing. It takes values from 0 to 2 pi. So you can represent the Berry phase as the angular orientation of an arrow. So at each point, place arrows with aligned at an angle that corresponds to the Berry phase, and what you obtain is something very familiar. You obtain the topological structure of a vortex, with the vortex core being precisely at the point where the gap closes. Now if I take, if either consider Thouless charge pump as a dynamical phenomenon or the spatial variation that I just described, you can think of this texture being embedded on either the temporal variation or the spatial variation of your system. So what we've done is, in this talk that I'm going to be giving, I'm going to embed a topological texture corresponding to what happens when you go around this, as you can see over here. So it's the arrow that tumbles with one particular winding. I'm going to be asking the effect of embedding this particular texture in the spatial direction. And I'm going to be asking what would happen if you take this texture and then eliminate it by tuning parameters such that the entire system becomes close to being homogeneous. Okay, so what happens, like I said, as you go from the state with the texture, you tune some parameter which I'll call gamma. The gamma is introduced in such a way that if you make gamma very, very large, it just favors the staggered chemical potential term. So the fermions are just localized on every odd site. Okay, so this is a free fermion system, so there's no excuse to not understand this completely well. So the easiest thing we can do is just take the first quantized Hamiltonian and then diagonalize it and see what happens to the spectrum. So here's a plot of what happens to the spectrum as a function of gamma. So gamma equal to 0 is when the system has a non-trivial topological texture. In other words, it has in its spatial variation a Thouless charge pump. Now as I increase gamma, you see that there are two things that happen. One is, if you can, I don't know whether you can notice this, there is this one mode that goes from the valence band to the conduction band, this diagonal line over here. So as you try to eliminate the texture, there is one charged mode that gets pushed from the valence band to the conduction band, and this is not too surprising. I had a charge pump, which means my ground side had an extra charge sloshing about, and I eliminate the charge pump, it pushes this particular charged mode to the conduction band. Even more surprisingly, when this charge mode is expelled to the conduction band, there is actually a many-body spectral gap that closes, as you can see over here. This is at finite sizes, so you don't see the gap completely close. That was intentional, so you can also see the charge mode going away to the conduction band. But there's a many-body gap closure, and there, in other words, there's something akin to a phase transition. This is what we want to understand. But this phase transition is not something that we know from other experiences. So if you look at the way the gap is closing at finite volumes, you realize that it closes not as 1 over L, which we get for a typical Luttinger liquid or metal or something like that. We don't even get 1 over L square, which is what you get for a Lifshitz transition, but you get 1 over square root of L. So the gap closes, there are infinite number of gap levels that close, but it closes with a scaling form that is not familiar from usual kind of critical phenomena. So this is also another thing, that something else that we want to understand. Alright, so let's just look at what happens. So there's a texture corresponding to walking along this path of the Rice-Meillet phase diagram and then just placing those coupling constants in your Hamiltonian. Now if I increase gamma, what happens is basically the texture corresponding to this circle gets dragged to the right. At some point the circle just leaves encircling this gapless diabolical point. So I must say that, since it's called a diabolical, this is called diabolical point by other authors, so we call this diabolical texture. So as the circle crosses this diabolical point and then becomes placed on the phase diagram without any gapless point in the center, we eliminate the non-trivial texture. So we realize what's happening at the critical point. It's this dark blue curve over here. The parameters pick out at some point on the chain the metallic state. So at some point on the Hamiltonian, at some value x star, the Hamiltonian is roughly described by an ordinary hopping model which corresponds to a metal. Right? So this is the gapless state. It's not altogether exotic, it's just a metal droplet in the middle. But actually, if you want to look at this very carefully, the correct description is not a metal. You can do, since we know that the gap closes at a certain point on your Hamiltonian, we can do a long wavelength expansion about that point and then look at what the Hamiltonian we get is. So the Hamiltonian we get is a 1D Dirac Hamiltonian coupled by two perturbations. It turns out that the 1D Dirac Hamiltonian has precisely two relevant perturbations, and both of them appear here. One is the point that moves you away from criticality, gamma minus gamma star. So this is the mass term. The other one is something that varies in space. It turns out that this Hamiltonian is formally identical to the Hamiltonian for Dirac fermions in a magnetic field. So this is the Landau level problem of Dirac fermions. The dictionary being, there's this length scale that appears, which is curly, the script L. The script L is analogous to the magnetic length in 2D systems, and x star is analogous to the guiding center. So it's just a formal analogy in the sense that the Hamiltonian you get is the same, but this is a one-dimensional system and no magnetic field and all of that. But in any case, this is a Hamiltonian we can diagonalize easily and get the eigenvalues, and from the eigenvalues we immediately get that the gap closes as 1 over square root of L, explaining why the spectrum closes in such an unusual way. So this is a description but not an explanation. A much more nicer explanation obtains if we realize that there is something that's known as trap scaling critical behavior. So this is something that people used to work on about a decade or so, 1.5 decades ago, where what people were doing was look at a critical gas that's trapped in a harmonic trap. So you have a harmonic potential and a gas that's at critical state, some Luttinger liquid or linear gas or some such thing, and they want to understand how the harmonic trap influences the critical exponents. So the outcome of this program is that in such a situation, when you have a conformal field theory or a scaling theory of any kind, perturbed by a slowly varying, spatially varying relevant perturbation, this introduces a new critical exponent that they call theta. Now the theta is not an independent critical exponent, it depends on the scaling dimensions of the parameter and dimensions and things of that kind. But all your length scales are renormalized by this new critical exponent, and with that you can do a new class of critical phenomena called trap scaling criticality. So it turns out that for our system, if you put in the right values, which is the dimensions and so on are 1, we get exactly theta equals 1/2, explaining the L square root of L that we had before. But it also explains the the connection to lambda levels. So, like I said, this trap scaling criticality can be detected using standard finite size scaling analysis. The only thing you need to do is, for finite size scaling analysis, you consider the dimensionless parameter to be distances, the position coordinate divided by your system size, which L. But now you just have to replace your system size with the new infrared length scale, which is L to the theta. So in our case, it's square root of L. So once you do this, you get a scale. For example, you can get finite size scaling collapses, the scaling of the gap with system size, and in fact, the correction to the Cardy-Calabrese formula for the entanglement entropy. So typically, you would have, if you going with by Sumilan's talk recently, you would have a formula that goes as C over 6 log L for a normal critical theory. But here you just have to replace L by L to the theta, and then you realize that you get the exact same thing. So it effectively renormalizes the central charge by a factor of theta. So this is the critical theory that we have here. Now, how stable is this? So we have distinct gap states with distinct topological textures, diabolical textures, and if you eliminate it, you encounter a critical point with its own set of critical exponents that I call a trap scaling criticality. How stable is this? This is a feature of the model that I had. It turns out this is not. You can introduce interactions, for example, nearest neighbor repulsions for the 1D spin chain, and by a straightforward Bosonization analysis, you can show that there exists a vast regime of interaction strengths where the same story continues to hold. In other words, your critical theory has exactly the right number of relevant operators such that this critical theory becomes completely stable. The only thing interactions do is that it renormalizes the new trap scaling exponent from 1/2 to 1 over 3 minus k, where k is the Luttinger liquid. So for k equals 1, we recover the usual non-interacting fermion limit and get theta equals 1/2, which I've been demonstrating using numerics. But for finite interaction strength, you get a new critical, you get a new trap scaling critical exponent and a new way in which your gap scales and so on. So it's very easy to see that this critical theory has no relevant perturbations left. You already saturated all of them. So any other term that you add can only renormalize the critical point or small changes to scaling dimensions and things like that. But the entire thing remains stable. So this phase diagram, what I demonstrated, is stable. But here comes a very curious question. For the symmetry class that we are looking at, which is U1 symmetry, this belongs to something called class A. And if you look at the table, class A actually has no non-trivial phases of matter. It's this thing over here. So what did we just find? Right, here is two states which are demonstrated as a critical point which is robust, and there's this nice picture of a topological texture, but it looks like there is no non-trivial phase of matter over here. In fact, there is no there's no something called fragile phase. I won't describe what that is, but we can argue it's not that, and there's no translation invariance, so it's not a weak topological phase. So what is this phase of matter? So to understand this, let's consider a new way of removing textures. Instead of making the textures very slowly in space, we can make these textures very rapidly in space by introducing a defect. So the texture very slowly in some range and then suddenly abruptly becomes 0 over here. So that's what this parameter beta does. It introduces a defect where the variation becomes abrupt. So if we increase this defect strength, what happens is that this extra charged mode that appeared through the charge pump gets localized at this defect and gets expelled from the conduction band, so the valence band to the conduction band. So it's not a many body crossing, but it's a charged mode that gets squeezed to a defect and then just popped out from the valence to the conduction band. This is not a phase transition. It's a normal quantum level crossing. It's like taking a gas and bringing an extra particle in. So if we look at the full phase diagram, I said begin with the state texture, increase the defect strength, and then there's this dotted line is supposed to indicate the charge getting squeezed to a defect and then pushed to the conduction band. But I also argued that this critical point where there is a many body level crossing is also stable to all perturbations, and in fact it is stable to introduction of this defect too, perturbatively. So this new critical point, in fact, if I introduce the defect and then increase the strength, becomes stable for a long time and then abruptly terminates. So at the cost of this level crossing, you can actually go from the state with texture to the state without texture by taking this large path without encountering any phase transitions. So if you were here for Vijay's talk yesterday, this is a phenomenon called unnecessary criticality. There are two regimes with different number of ground state charges, but these ground state charges are not a good quantum number. Charge density remains the same, but there exists a path where there is a thermodynamic singularity of a phase transition, but there exists a distinct path where you can avoid all kinds of singularities. And so this is what is called an unnecessary critical line. In fact, I think this is, as far as we know, this is the first example of such a phenomenon in free fermionic systems. Okay, so we can put all of this together and also change chemical potential. So all the introduction of chemical potential does is it takes these two critical lines and then it opens it up to metallic phases. So it takes these critical lines and opens it up to islands of metallic states, but the rest of the phase diagram remains robust. So I'll just quickly say a couple of minutes about generalization and then end the talk. So I apologize that this is going to substantially raise in the level of mathematical abstraction, but hopefully I'll be able to convince that this is actually a useful thing to study. So what we have done is, in introducing these textures, we have married the topology of real space of our lattice to the space of all possible ground states, which I have represented using this caricature over here. So you vary parameters as you go along in space slowly, that you chart an interesting path in the space of theories. That's what you want to do. So it's a collection of smooth maps from real space to the space of theories. This induces something that we can track much nicer. It's a map between what are called homotopy groups of the real space and homotopy groups of the space of theories. Still a very complicated thing. What is the space of theories and what is the topology? We don't know that. But this is where we invoke a conjecture that Kitaya made about a decade ago. So it's a technical conjecture, but it's a very, very useful and interesting one. He conjectured that the space of theories in various dimensions form what is called an omega spectrum, which endows to it a collection of very interesting and useful properties. So I say this is a conjecture, but actually last year there was a paper that was put out by Yosuke Kubota who claims to have proved it. Nevertheless, so the upshot of Kitaya's conjecture is, for each cycle in your real space, as you go along the cycle of a torus, the texture that you embed to it is labeled by a lower dimensional phase of matter. So an n cycle is labeled by a d minus n dimensional phase of matter. Now this is a very opaque thing to say, because how is a texture in d dimensions related to a lower dimensional phase? This turns out is the relationship between charge pumps and charges, a generalization of it at the very least. In any case, we can construct explicit models and write down how to write these textures. I'll just give an example of what this will tell you. So if you consider 2D P plus IP superconductors and their generalizations, like superconductors without any additional symmetries except for fermion parity, you can actually argue that the textures look like this. At the very basic level, the system can correspond to some P plus IP superconductor. That's this piece of information over here. On each one-dimensional direction of the torus, as you go in the x direction or the y direction, you can pump what is called a Kitaya's Majorana chain. So you can pump a Majorana chain. On two-dimensional textures, you can have a pump of a fermion parity pump. It's a particular thing, but these are all correspond to some interesting textures. You can write down a model that has all of these things, or one of these things, or many of these things, and you can write down parameters to tune such that one or more of these textures is eliminated. Each of them will result in a distinct trap scaling critical transition and produce interesting phase diagrams of the kind that I mentioned before. Okay, so that's the example. Okay, I don't know why that happens. In any case, so I'll just summarize. We have a new class of topological phenomena protected by spatial textures, which we call diabolical textures. This introduces a new class of critical phenomena, and there is some dimensional transmutation from one dimension to the other. So for future work, we want to see if these textures can. So what we essentially achieved is the ability to do away with tuning one parameter by introducing it as a texture, and we want to see if this can stabilize other kinds of interesting correlated states. We also want to ask whether this is important for experimental settings where there exists naturally slowly varying textures in your system, in particular flat bands through twisting and things like that. There's some preliminary analysis to suggest that this is very intimately connected to the emergence of flat bands in a natural way. Also, one could ask whether if we can vary I told you how we can start off with a slowly varying texture in time and then move it to space. We could also ask whether we can have slowly varying textures in both space and time, and that can result in new kinds of phenomena, which gives you new kinds of non-equilibrium phenomena. So with that, I'll end my talk, and once again, this is the preprint if you're interested in it.
same way they're starting to do this space thing, right? Yeah, so like there, of course, you have to this adiabatic concept. So here also you have something like that. Right?
Yes,
So
yes.
you're approaching the critical points. Is it like this trap scaling? Is it something like Kibble-Zurek type thing, or
It
you can
the
think of like that?
Kibble-Zurek is avoided criticality. So in this picture, it should not, it won't be obvious, but this is like Kibble-Zurek. This line, this is actually a distinct thing that I don't think correspond to Kibble-Zurek.
Yeah, so just a little bit of a doubt and a clarification. So you said about avoided phase transitions in this which is like unnecessary. So does it like pencil the point, the diabolical point as a necessary transition?
I don't know.
Like, intuitively it follows a little bit of a similar definition of penciling and all.
Very likely. I don't fully understand that, but I don't have any intelligent comments to make, but very likely.
Any other questions or comments? All right, so yeah, let's thank